Hello everyone, I want to use this video to give you more instructions on our Lab 2, Earth-Sun relationship and solar radiation. In this lab, as you can see, you will have 4 questions. 3 of them I think is about Earth-Sun relationship, and the last question is about solar radiation. So the first question is to ask you to draw. Okay, so you want to maybe print it out, okay, print this lab out and then to draw on the paper, or you can just use your mouse to draw on this electronic document. Okay, so you will have a few sub questions. The first one is on each of the 3 blank diagrams. You can see down here you have 4. I finished the first one for you already. You just need to draw on this one, and this one, okay, on each of those 3 blank diagrams, and draw and label both the names of the parallel and latitude angles. Okay, so you want to basically mimic what I did here. So to recognize, to measure, well, where is your Tropic of Cancer? We learned that in the first module, right? So what's the degree? What's the degree here? Okay, you want to measure that. Basically, this is the degree of your Tropic of Cancer, right? And this is the degree, if you go all the way up here, that is the degree of Arctic Circle, and so on and so forth. Okay, so you want to mimic this. I will measure your angle drawn here. You cannot just like eyeball that. Okay, so you can see here, North Pole, South Pole, you labeled it. Okay, equator, you labeled it on your blank diagram where it is. Okay, and those circles. And the last thing may be a little bit challenging, that is the circle of illumination. Okay, in our study guide, you have a video to show you what is the circle of illumination. Well, basically is you ignore everything. You just treat the Earth like a ball. Well, the sun just coming from one side, right? Because our Earth is round. Our Earth is round, it's a ball. Those parallel rays, okay, sun rays, can only illuminate half of this ball, right? Okay, the other side will be in the dark. So the lines separate the bright and the dark. That is the circle of illumination. So you can see on my example, well, on this day, June solstice, you have your circle of illumination just, it's connected. It passes circle of Arctic Circle and Antarctic Circle, right? And in this case, that is the December solstice. Then where's the circle of illumination? Actually, it's very easy because ignore all these. Circle of illumination is what? Perpendicular, 90 degrees to those parallel sun rays. So you just need to draw a vertical line to those parallel rays, but this line need to pass the center of the Earth. Circle of illumination must pass the center of the Earth. So you can see here, must pass because the Earth's axis is tilted. Well, that is why on June solstice, you have the entire region within Arctic Circle in the bright part. Okay, and the entire part of within the Antarctic Circle is in the dark part. That is, give us the seasons. Okay, so what would happen on December solstice? What would happen on March equinox and September equinox? Okay, remember, circle of illumination always perpendicular to those sun rays, but pass the center of the Earth. Okay, so give you a hint. And then the second question is, I want you to use a solid dot, like you can see here. I should use red dots, but this is the vertical ray. Where the vertical ray strikes the Earth's surface. This dashed line is the Earth's surface. Okay, it's a tangent line that is the horizon ground of this at this latitude. Well, this point we call that subsolar point or declination of the sun. Okay, you can look it up on certain day, any day, okay, where this point is by using the very last chart on this document, this so-called analemma. Okay, so for example, today is January 13th, so let's find January here. January 13th is about here. So today that dot is at about like 21 degree, I would say 21, almost 22 degree south. Okay, so you can see this is a calendar for you. This is the calendar for you to look it up on certain day where this solid dot declination of the sun is. Okay, remember how to use it. It's just this calendar, and you're going to find on certain days later in a later story, in a later assignment. Okay, so that is the thing. You want to use the dot to mark this subsolar point on those three blank diagrams. Okay, this is the second question. Okay, and then yeah, I think that's it. That's the first question. Okay, use the analemma and use your ruler to draw on the first question, those three diagrams. And the second question actually asks you to calculate the solar altitude, or how high the sun is above the horizon. So you can see this is the horizon, okay, and this is the angle, right? At any other latitude, okay, not just those very typical, circle of illumination, tropical of Cancer, tropical of Capricorn, and so on and so forth. For example, if you want to calculate the circle of illumination, the solar altitude at LA, okay, our latitude, let me tell you, that is 34, okay, then you will plug in observer latitude, okay, 34 degree north. North, you use positive like what you did in the first lab. Okay, and the declination of the sun on certain day, right? Today is January the 13th, and then this one is at where? Is at 21 degrees south, right? So you should use negative 21 plug in here. Okay, so 34 minus negative 21, then you get your answer, right? And then this ABS, that is gets the absolute value of the result. So basically you just turn everything positive. You cannot have negative out of the absolute value, right? So 34 minus 21 should be 55, right? It's a positive value, then ABS, absolute value of 55 is still 55, okay? And you use 90 to minus the final result here, okay? So your the angle at LA today should be 90 minus 55, then that is a 35 degree. Okay, so today if at noon we measure how high the sun is above the horizon, okay, that is 35 degree, okay, at LA. Amazing, right? Okay, so here I give you another example, I think. Okay, another example, absolute difference between observer latitude and declination of the sun. Okay, read it. Okay, read it. Okay, so here is your example. Okay, here is your example. So to calculate the analemma. Okay, and then when you calculate it, you want to here solar altitude of LA at on each 22nd of each month, you record it here. You do this calculation for each recording, for each day. And remember, you need to show your work. I see many of you on Lab 1 didn't show work on your math scale. Okay, so you need to show your work. And then when you have this, you want to plot. Okay, in January, February, on the 22nd of the day, of the month, okay, how high the sun is, what's the degree solar altitude in degree on the 22nd day of each month. So you can just plot it here, for example, January, for example, today is 35, so you go here, plot 35. Okay, and then feel free to connect them. You will see a curve that is a solar altitude change in a year at LA. You can do this for your favorite place you shared with us in our discussion board week 1. Okay, so which is very, very interesting. Okay, and here the third question basically carry on that dot. You can see this is the day length. Okay, in this question we examine how solar altitude change within a year, but in this question we examine how the day length change within a year. Okay, those two factors determine how much solar energy we get in a year. Right? If you have a longer day, if you have a higher solar altitude, okay, the sun is more concentrated on the ground, you will have the total amount of solar energy very high. Okay, so you can see different curve here represent different location. You have equator. Let me make it larger. Okay, you have equator in this solid line. You can see never change, always 12 hours. Okay, but Honolulu, go a little bit to the north. Hawaii, you have this dashed line. It changed a little bit. It's quite stable, right? Okay, and then LA is the next one. This a little bit thicker. This dashed line. Okay, this is LA. This is the day length. It's not solar altitude. Okay, and then this dash dot line, that is New York City. You can see when you go to the north. When you go to the north, you have more and more dramatic day length change or drastic day length change, right? Meaning your longest day minus your shortest day, this difference become larger and larger. As you can see, when we move to this, oh my gosh, what's this? This is your barrel in Alaska, 71 degree north. You can see during the summer, very short summer, by the way, you have 24 hours in Alaska Barrel. You have 24-hour day length. The sun never set. But in the winter, you have 0. You have nothing. Okay, North Pole more extreme day length change. So you can see here longer period. Okay, actually from this so-called Julian day. That is another concept. Let me explain in a minute. Okay, but from this 80 Julian day, you have 24 hours lasting for 6 months. Okay, this is how many days? 180 days, right? That is a 6 months, 24-hour day, and another 6 months, 24-hour darkness. It's just dramatically. The next day, you don't have any sun. Okay, just have one sunrise and one sunset. One sunrise here, one sunset here. Okay, it's amazing. Okay, so then what is Julian day? Julian day basically is you count the entire year. I should cut off my diagram here. 300 in total you have 365 days, right? Okay, you count from very first day, January the 1st, that is the number 1 Julian day, and so on, right? And the last day will be 365 Julian day. Okay, you can look it up. You can click on this link that will lead you to the document Wikipedia to explain. Okay, and you can go to NASA to check what is Julian day today. Okay, and then when you make an observation like what I just guide you, okay, when you move to the north, you have more and more drastic day length change, right? And then answer those questions. How does this day length change at equator? Describe it. Okay, how does the day length change in northern hemisphere winter Julian day between 0 and 80? 0 and 80, and after this about like 265 day. Okay, so when you go to the higher latitude, how the day length change? Okay, read the question. And how does the day length change in northern hemisphere summer? So basically between those 2 days, 80 and 265, this period. When you move from equator to the north, Okay, equator, Honolulu, LA, New York, Barrow, Alaska, and North Pole. Okay, how the data change when you go to the north. Okay, and then let's see, on the 2 equinoxes, those 2 days, how does the day length change as you move from equator to the North Pole? So you can see here 80, 20, 2060, 20, 265. Well, all these curves, they come together, meaning they have the same day length, right? That is why we call those 2 days equinoxes. Everywhere, day lengths, they're equal. Why? You did it in the first question, actually, because on those days, those are the 2 days. Okay, your circle of illumination and the Earth's axis overlapped. Your circle of illumination evenly divide all the latitude. Okay, every place, everyone have half in the bright part, the other half in the dark part. By the way, you need to shade the dark part in this question. Okay, just mimic my example. Okay, so that is your observation on those 2 days. Okay, and then the last question. Okay, it's about solar radiation. We know how the day length change at different latitude. We know how the solar altitude change at different latitude. If you want, you can plot any latitude, right? Then I want you to apply those understanding, okay, your observation to understand this map. So you need to open this map to see the map of the annual total solar resources available at the Earth's surface in Americas. Okay, so let's go here, and you can see there is a map, okay, produced by National Renewable Energy Lab, I think. Yes, National Renewable Energy Lab, yes. So this is a map. Okay, we as a geographers, we always use map. So I want you to read the data summary. Okay, for any map, you need to read the data summary. What data is used to produce this map? Okay, and of course your map key. Okay, this is kilowatts per hour per square meter per day. So basically, that is the solar irradiance. That is how intense, your the density of the solar energy, okay, received on that day, every hour. Okay, so you can see when the color become darker, become redder, you have more solar energy received per every square meter, right? So then let's go back to our question. Okay, so remember, it considers the effect of the cloud. Okay, based on what you learned in the previous 3 questions, the pattern, the spatial pattern of the total solar resources affected by day length, altitude, and how they change in a year, right? So I want you to describe the spatial pattern of total annual solar energy in Americas. So basically, what is spatial pattern? I will provide you another video on our lab page. Make sure you watch that. What is spatial pattern? Okay, but long story short, where is the highest? Where is the lowest? And as you go, in this case, from equator to the north, from the equator to the south, how they change in general. Okay, let's just consider latitudinal change. Okay, and then if you want, you can see, well, because this map consider cloud effect, well, those patterns, it's not just, like horizontal stripes. You have certain changes, right? You consider the weather. So why in these places, Baja California, Mexico, you have the highest, right? And then in our Texas, Arizona, LA, including ourselves, okay, we have the highest. But when you move to the east part of the country, because Florida, they rain a lot, right? So you have relatively less. Okay, so I want you to describe from equator how the things change and the local pattern. For example, compare Mexico with the Caribbean islands, compare LA with the eastern part of the country, right? So you will see the cloud effect. Okay, so I want you to describe this pattern. Okay, describe this pattern. And same thing, you can see, very interesting in in South America, in Peru, these places, right? Versus Brazil, you have the rainforest, you have less. But this part, you have more, right? Okay, so describe it. Okay. And this is the first question. The second question is apply the concept of the day length and solar altitude to explain the pattern shown on the map. Why? Explain. The first one is describe. You just describe what you see. But here is the question, why? Okay? Don't mess up those two concepts. So why? Why Mexico have the highest? Why Mexico have the highest? Right? Okay, why equator? Well, you don't have the highest, right? Okay, consider why it's like that. Okay, consider cloud, give you a hint. Okay, but in general, when you close to this tropical area, in general, you have the high values. But when you go to the north, you have the low values. Why? Consider solar altitude, where you see more concentrated solar energy, where you have the lower solar angle, you have less concentrated solar energy, right? The day length, well, where you have the constant day length, well, where you have the very dramatic change of the day length. Okay, so that is a hint for this one lab. Okay, I hope you enjoyed it. Sorry, let me come back. Okay, so this is this lab question. Remember, the last one is just your analemma. Okay, it's your analemma. So you will be working with the same people in your same group. Okay, same group leader. Okay, so make sure you respond to your group leader, his or her, emails or Canvas message. We should appreciate our group leaders. They take extra time to try to organize your group meeting to work together. Okay, so this is our lab 2. Okay, so that's it for this lab, and I will see you in the next video.